Hello, and welcome to our talk about how we achieved the microcode execution inside modern Intel CPUs. There is some confusion with this term mobile CPU because you have laptop, you have desktop, and really you also have system-on-chip Intel's CPU platforms. And in this case, we are meaning Apollo Lake and Gemini Lake platforms, system-on-chip platforms, Intel's. Yeah. And our research team includes three researchers: Mark Ermolov, Dmitry, Sklyarov, and Maxim Goryachy. This is me. Dmitry and Mark are working for Positive Technologies company. Unfortunately, Mark couldn't be here. And I'm not affiliated security research right now. As you maybe know, we have been researching Intel's platform for almost 5 years. During this time, we found vulnerability in Intel management engine. We found undocumented hub mode for disabling Intel ME. Also, we're researching some internal Intel technologies like Intel Visa, Intel debug capability interface, and many other security features. But how exactly the Intel microcode works has been the almost interesting thing for all of us all this time. And the last year, we finally got it. We found the way to execute arbitrary code inside the CPU, and it allows us to change instruction behavioral. Today, we will briefly discuss what is microcode is, how it's used in modern CPUs. We will tell also to you how our research went and what approach we used, how we created the disassembler for an unknown architecture instruction set. With this disassembler, we found undocumented commands, and we are able to decrypt microcode updates. Let's start. Okay, so on this picture illustrated the availability of documentation for Intel's technologies. The deeper we go, the more difficult it's to get documentation for external researchers. For example, you just can download documentation, you can download the instruction set manual from Intel's website. VTD has official documentation with detailed interface description. But unfortunately, information about the Intel management engine or the boot guard technology are available only after signing non-disclosure agreement. And it means that microcode and internal architecture are trade secrets or even top secrets, and it are available only within the company. It means that only internal engineers can understand how modern Intel CPU works. So, as I said, we have been researching Intel's platform for several years. On this slide, you can see our previous related works. If you want to know more details about internal buses, internal architecture of the modern CPU, you can find information about it in our talk related with Intel Visa. About JTAG and debugging management engine, you can you can find information about it inside Intel our talk on CCC about how we achieved JTAG for Intel management engine. And so a few words about microcode. Microcode is a layer for hardware level instruction that implements high level machine code instruction. In general, microcode is located inside the CPU and it manages command execution for high-level code instruction. It also initializes internal processor and devices and buses. It looks like a bring up code inside your CPU chip. As we think, microcode partially implements some technologies like virtualization technology, virtualization support, HG, HGX, MPX, TXT, and etc. Microcode is strongly associated with the internal CPU architecture. For example, the number of pipelines, cores, and decoders determine microcode too. This means that microcode differs between generation of processor. And if the microcode has been researched for one generation, you need to do this work again for another generation. For example, if you understand how it's worked on Skylake, you need to do it again for Ice Lake or Tiger Lake platform. Okay, so for example, on this slide, you can see internal architecture of Intel Skylake CPU. You can see that structure is not simple. CPU has internal devices, buses, and internal communication with caches, and we are interested in this part. Here are some different commands which, as we know, are transformed into microoperations. And these microprograms are directly executed. They are special blocks or devices that executed microcode operations. And we have the one question: how does they work? And we know that we have ROM inside a CPU, and it contains a fixed program, and it implements a complex instruction like CPU ID. As you know, this instruction returns information about your processor, available features, and this instruction shouldn't execute on ALU. Also, sometimes you need to update this ROM code. And for these purposes, processor has a small RAM area, and microcode updates are stored here. But you have one challenge: how to apply new changes to read-only memory. I mean that how implement updates for ROM area. To solve this task, in the processor, there is a special microcode sequencer. It has mass path register, and this register contains two addresses. The first addresses, it's addresses in which you want to intercept execution of microprocedure. And the second address, it's address of the patch inside the RAM area. The microcode decoder is comparing on each step current addresses with match patch registers value. And if the value are equal, the microcode transmits the execution sequence to the corresponding instruction in the RAM. It means that it looks like a hooking function when you just splice the first instruction set. And This approach allows you to flexibly change the behavior of the macro-operations. We didn't know vulnerabilities such as Meltdown and Spectre are fixed in this way. Intel just released a new version of the microcode. The content of the ROM and the micro-operation format are what interested us in the first place, because it's the if you know it, you can examine the whole platform. Okay, so how can we get to them? And we saw two approaches. The first approach is hardware. And in 2017, a research team from Rock University published an amazing paper about reversing x86 microcode for AMD CPUs. In this work, they decapsulated AMD processor and restored the ROM code by examining the chip with a microscope. They developed special small operation system, and they did fuzzing of microcode operation for understanding how it relates with high-level instruction. Also, in result, I highly recommended reading this paper, and this research team could do it because the old CPUs, AMD CPUs, didn't have integrity or crypto protection. This allowed you to create your own microcode updates, but that wasn't our case because Intel microcode has an RSA signature and it was encrypted by an unknown algorithm. But we found another way. We had found to another way. But how can Intel engineers debug microcode? The answer was obvious through JTAG. And in 2015, Intel released a new debug subsystem for low-level debugging called DCI. Before it, you need the special platform with special socket and special devices for debugging your platform. But after that, you can get market platform and activate DCI debugging, and you can debug your own operation system, UEFI firmware, and another application. This allows you to debug the platform via USB interface. We had a lot of experience with this adapter, and when we researched Intel Management Engine, this helped us to get access to CPU debugging as well. Early on, we found a vulnerability in Intel Management Engine, and we are able to activate JTAG for another Intel chip, PCH. Inside this chip, you have the small x86 core, and the Intel Management Engine on the modern CPU, unfortunately, doesn't have microcode, as we understand. But maybe everything has changed on isolate platform. But we didn't find an exploit for it. Main idea was, okay, so we can hack x86 core inside PCH, and maybe we can recover microcode from this core, but it doesn't work. From public version of Intel's debugging software called Intel System Studio, we knew that all chips have a special device DFX. And also, this device, you can unlock your platform through the special password, unique password for each platform. And this device, DFX device controls the debugging capability and allows you to unlock microcode access through these registers. But as you can see, the password is 72 bits, which is quite a lot to brute force, because you need, for unlocking your platform, you need to push your password to register, to initialize some subsystem, and to activate and lock. If password is not correct, is wrong, in this case, you need to reboot your platform and try again. You spent about few seconds on this cycle, and 72 bits, it's enough for protection against brute force attack. But on the slide, you can see a diagram of modern Intel platforms. Desktop and server PCH and CPU chips have independent DFX devices. We knew it from their configuration, from Intel System Studio configuration. But this means you need two passwords for the platform to debug it. Password for PCH and password for CPU to activate the internal level, Intel's level debugging capabilities. But in system-on-chip platforms like Atom, Celeron, Pentium, you have only one DFX device. We found only one DFX device in Intel System Studio configuration. And the main question is, if SOC has only one password, does it mean that unlocking the management engine leads to unlocking the CPU? I mean that that signal from this DFX device unlocking not only PCH and an E-core, but also on-core and main core of the CPU. And it was funny because we published proof of concept for in E about two or 3 years ago, but only after 2 years we can check it and we can answer on this question. And the answer is yes. If you unlocked PCH for system-on-chip platforms, it's also unlocking CPU too. But it was only half of the story. Dmitry will tell you how we developed our disassembler. Thank you.
And now it's my part. I will tell you about how we reverse microcode and get results that we publishing to you right now. Using some techniques that Maxim describes earlier, we achieve capability to read internal system bus. So we have some really very little information about what it is and what information it should contain. But in some description for all platform, we find that there are some method to get data, and we start brute forcing addresses and find 5 arrays. And we discovered that first 2, they labeled array 0 and array 1, are read-only arrays, so we could read them but couldn't write back to them. And 3 other arrays are read and write enabled, so we could modify information in them. And we have ideas that they somehow related to microcode. And you could see that information in first 2 arrays have some features. For example, you could see that there is 3 words with some value and the last 4th word always 0. And in the second array, all 4 values in each line are the same. So it's not mistake. Probably it's the way how controller represents information to us when we read them. And after looking on data and perform analyzing, we discovered the way how we should represent that arrays. Actually, first array with 3 words with values and fourth one with 0 is opcodes ROM. So it contains operation codes for instruction for microcode, micro operations. And the second array with identical values in 4 positions, it's a sequence word. It's a kind of instruction how to use 3 operations simultaneously and how to perform next steps, where to jump, or some other conditions. It looks like microcode have 3 separate execution units, which operates on operation 1, 2, and 3 in the same time, and sequence word tells how to thread the results of such executions. And 3 read-write arrays are sequence word RAM, which use it for patch data, and we discovered then when we write some data to sequence word RAM and read back opcodes ROM, we have updates in some late addresses of that array. And the same with opcodes RAM. So we could modify data in read-write areas in last 3 arrays and see how they reflect updates in first 2 read-only arrays. And match-patch array, Maxim already said how it works. It contains pairs of addresses, address at which execution should start when match-patch works. So if you have some instructions that start, for example, at address 1000, and first word in match page record is 1000, then you need just jump to address that stored in second part of match page array. So you just change the code flow of execution instruction in any place using match page array. And after a lot of tests, using JTAG, we have a great advantage against people who make hardware reverse engineering of AMD microcode. We have debugging capability at very low level. We're able to execute any instruction on central processor and see how it reflects execution inside microcode. So after a lot of research, we generalize micro operation format. You could see that there is source and destination indexes, index of registers. There could be some immediate values that stored inside the instruction, opcodes value, parity, and some other bits that controls how instruction executes on some microcode core. And sequence word format tells how to link together data modified by each instruction and on which condition make jump to which address. Here is address inside the microcode. So using this field, you could just jump to any place after executing this instruction. It's like execution using predicates, so you have address of jump and jump on it if some predicates is true or false using conditions that specified in other fields. And actually, to rebuild this information, this structure, it was very complex task performed by Mark and Max. I mostly not participated in this part of research. And to check that we really could modify microcode, we decided to modify CPU ID instruction. It's a good idea to use this instruction because we knew for sure that some leaves of CPU ID are implemented in microcode because they could be updated using microcode update. So when we discovered that Intel released patches for vulnerabilities like Spectrum meltdown, they reflect in CPU ID behavior. So we start trying different approaches and find the match address where some leaf of CPU ID instruction is called. And we start trying to put instructions. We have very little idea what each instruction does, but we start trying them to perform something meaningful. And finally, we achieved ability to display name of processor generation with the value that we provide. So we modified 3 arrays which are available for writing, and this reflects in the modification of CPU ID instruction that available from central processor. And that demonstration was proof that we understand our finding properly. After that, we obtained a lot of bytes and some idea how we should interpret them, but actually it's very hard to analyze. So again, we start developing some tool that allows us to analyze the code, the microcode. And at that level, we start developing disassembler for microcode, and you could find it in our GitHub. And now I will tell you about microcode update. Actually, it's not too much known about microcode update. We knew that it could be loaded at different stages of execution during UEFI startup routine, during inside running operating system, and so on. We knew that microcode data are encrypted, but no public information is available, which algorithm is used. When I have discussion with some people who are interested in that area near 5 years ago, they have suggestions that microcode updates encrypted by IE's Advanced Encryption Standard algorithm, but there was no cons or pros to prove that. And it was well known that update is protected with RSA 2048-bit signature. And actually, microcode updates, they included in BIOS updates, so there is ways to extract them. Some people already collect that information and have some archives with different version of microcode for different types of processor architectures. And I look inside that files and analyze the headers and discover information about internals of headers of microcode update. And for sure, after that, I discovered that that information is documented by Intel, but unfortunately, there are not too much information inside that documentation. So you could find information how to find for which CPU type this microcode is applicable, and almost nothing else. I discovered where in files there is signature, but again, I could verify the signature, but I have no private key. I can't sign it by myself, and I can't decrypt the data. So this information is not very helpful. And finally, when mostly Mark developed perfect disassembler, I believe he understands almost every instruction in Atom microcode. So he creates a great tool that allows me to read the text, not analyze the bytes, but analyze the instruction. Instruction are not like Intel x86 instruction. They have very long names in Mark interpretation. And on this slide, you could see on the left part, you could see the compiled code that I find inside the decompiled, disassemblered microcode. And there is a lot of some actions, but if you will try to interpret every step with some care, you will recover a very simple algorithm. It could be seen on the right part of the slide. And actually, if you're interested in cryptography, I'm sure that you knew the name RC4. This algorithm was very popular more than 20 years ago. It's a stream cipher with very simple code. It uses no constants, is very short in implementation, and you could see code for decrypting data with RC4. And there is another part of RC4 for setting the key, and that's all that you need to decrypt the data. Actually, beside set function and decrypt function, you need the key. And I find the key by analyzing another part of the microcode. It's not representing on the slide. Actually, I start with the idea that some encryption usually involves hashing. So to decrypt data, I need to provide the key, and key is not constant, should be not a constant, but some value evaluated using the hash function. So I'll start looking for hashing constants, find the constants related with SHA 2056, and that was start point. And carefully analyzing the code, I find this place. I recover the algorithm for getting the key, and finally we decrypt the microcode update. You could see on the slide that many bytes are 0, so it's not random value with huge entropy. This data entropy is very little, so we decrypt data properly. And actually, these bytes are bytes that written to 3 arrays available for writing, so it's data for microcode update. And a little bit later, we discovered that not only old version of Atom that we used for starting our research have some vulnerability, but we discovered a new vulnerability for Gemini Lake CPU architecture. And using that vulnerability, we were able to obtain read unlock on that platform. And again, it's SOC, system on chip. So we were able to unlock not only the management engine, but also the central processor. By the way, Intel calls this not read unlock, but Intel unlock. But we use read unlock for many years, and we still use this name for simplicity. Little bit later, we discovered that there are at least 2 instructions that not documented in any public Intel guide, and you could enable them if you have read unlock on the platform. You just enable them using write to some model-specific register after performing the unlock of the platform, and using that instruction, you have ability to read and write data from that arrays that I noted at the start of my part. So using it, you could read the microcode, and for sure you could modify the microcode. So there is a way to modify behavior of the computer system from the running system, and its modification would not be noticeable from the operating system level. So you will be not able to find that something wrong with your microcode if you don't know how to use these registers. So it's actually a very interesting capability. By the way, it seems that one of common devices that use either Intel Gemini Lake or Apollo Lake processor is Tesla cars. So if you own one, you could try to perform some researches, and probably it would be interesting for you. Also, when we look inside the microcode update after decryption for gold mount, we discovered very interesting thing. There is an ELF file inside the microcode update. Actually, we don't know what it is for. For sure, it's not executed on the microcode engine. It's executed on the central processor, but it's inside microcode update. So it's very interesting way of design some patches or some internal features for central processor using ELF files inside the microcode. And you could find almost everything that we noted in this presentation in our GitHub. There are several repositories with microcodes that we dump from gold mount, some disassembler, and so on. It's a very good point to start if you're interested in research for microcode. In May 2021, Intel announced a bug bounty program for microcode. So if you find the bug in Intel Pentium Celeron or Intel Atom processor, you could get some money. And 10 years after Intel announced the program, we published our disassembler. So probably our disassembler will help you to make this research. This program active till May this year, so you have some time if you're not started yet. Also, after our publications, Intel, without any reference to our work, published some description of how microcode work relating to SGX, to internal technologies that allows you to perform operations securely even on, for example, cloud environment. And they called it XU code, and you could find this information on Intel site, but actually it's not very deep, so it's just explanation how it works without any details. And finally, first step that we performed is achieving very big level of debugging capabilities that we called red unlock, that allows us to do almost any debugging thing with CPU and management engine and microcode too. Also, we recovered almost every microcode upcode for Apollo Lake. For Gemini Lake, we not developed the microcode disassembler because it requires almost the same amount of efforts. So every processor architecture has their own microcode, their own instruction, and probably even their own way of interpret fields inside the operation or sequence words. Also, we demonstrate that we could modify microcode on the fly without writing to SPI flash or something like that. And we find undocumented instructions that allows you to do it using from operating system from running computer. So probably, I believe that it's all that we have to say to you today, and I want to say thank you for Mark Ermolov. Again, unfortunately, he wasn't able to talk today, but his impact on our research was really significant and dramatical. And thank you.